Alright, well, welcome back. We're excited to hear a nice talk here about the broken stick problem in higher dimensions. This is Alex Page, Yulia and Rose Hulman. Alright, thank you for introducing us. We're a group from the Illinois Geometry Lab at the University of Illinois. As Christine said before, this is Alex, I'm Yulia, this is Yi. Our faculty mentor is Emtit Kalbibun, and our actual team leader is Dr. A.J. Hildebrand, both also from the University of Illinois. So just an overview of what we're going to talk about today. We're going to tell you a little bit about the broken stick problem in its original form, the broken stick problem in higher dimensions. Then we're going to talk about how we generate the random pieces for broken stick problem. We're going to tell you a little bit about our results, some applications, and we'll make some conclusions.
Okay, so like Yulia said, our project is based off of what we call the original broken stick problem, which is as follows. Take a stick of length 1, or really any length, and you pick 2 random points, x and y, on that stick. Now, you break that stick in those 2 points, giving you 3 pieces, and you try and form a triangle. Now, it's not always possible to form a triangle, so our question is, what is the probability that the 3 pieces will form a triangle? And this was brought up by an exam in Cambridge University in the 1850s. So, anyone have any idea what the answer could be? What do you think?
Fourth.
Why do you think that?
That's a random guess.
Any other guesses? What do you think?
1/2.
Do you have any reason for that? Any more guesses? 3/4 and then?
1/3.
1/3, all right. Okay, so the answer is 1/4. That was, sorry. So the solution to that can be derived from the triangle inequality, which we know is the lengths of 2 shorter sides of a triangle must be greater than or equal to the length of the largest side of the triangle. And so using the solution here, we can imagine, is this stuff? Okay.
These are technical.
Please stand by. We can imagine x and y, which are the points on the stick, being points in a coordinate plane. So they have to exist within the square between 0, 0, and 1, 1. And so then we just find the region, which is all the points x and y, such that you can form a triangle from breaking the stick that way. And when you calculate the area and divide it by the area of the entire region, which is conveniently 1, you get 1/4. So that's the basic derivation of that answer.
Okay, so this problem is pretty trivial if you just draw it out, and it was actually something that was solved in the 19th century, so that's not what our research was about. We decided to take it up a notch and take it up a dimension and think about forming a tetrahedron. So if you break up a stick at 5 points, now you have 6 sticks, and we try to form a tetrahedron with the pieces. So our first question is, what is the probability that we can form at least 1 tetrahedron with the pieces? And then the next question is, what is the probability that these 6 pieces actually form k incongruent tetrahedra, where k is between 0 and 30? He will talk to you a little bit about what it takes to form a tetrahedron.
So as we know, the tetrahedron has 4 faces, which the 4 faces are all triangles, so we need to satisfy at least 4 triangle inequality conditions. So our question for forming a tetrahedron is, what is the probability that 6 positive real numbers form a tetrahedron? And this is the special case when n equals to 4 for the distance geometry problem, which we will talk about later. So as you can imagine, if we want to form a tetrahedron, at least we can have a net like this to form the tetrahedron, and all the edges that can match up. As Alex is pointing, those edges are of same length, but this one actually does not form a tetrahedron.
does, but it seems like it would like be totally flat, but that's because this is not super well made.
Yeah, so seems like the net is not the only condition that we need to satisfy. So there's another condition, which is more theoretical. This matrix is first appeared in Dexter and Walker's paper in 1987. At first, this is a n-dimension thing, but we simplified it as a three-dimension function and applied it to our tetrahedron. So if we have a certain permutation of tetrahedron, the lenses A, B, C, D, E, F, and we put them into this matrix, and after we calculate those eigenvalues, and if we got three non-negative eigenvalues and plus the net condition, with these two conditions, we can make sure that we can form it.
Okay, now that Yi's talked to you about what it takes to form a tetrahedron, I'm going to talk about how we form these random pieces, and Alex is going to demonstrate. So we considered three different methods. First, the classical broken stick method, then the sequential broken stick method, and finally the independent random method. So in the classical broken stick method, Alex is going to choose 5 random points on the stick, so hopefully he can actually mark them. He's having a bit of trouble. Okay, so now that we've picked these 5 random points, you would break them simultaneously. Obviously we can't do that, but you could just go along the stick and break them. Next is the sequential method. You also start with a stick of length 1, and then you pick a random point on it and break it. So then you would choose the larger portion.
Which one's bigger?
Right.
Left one?
Okay, so the probability of them being exactly equivalent is 0, and so you choose the larger of the pieces. Now you break on that piece. So once again, the probability of them being exactly equivalent is 0. Which one's the biggest one? Come on, you guys know the answer to this question.
Middle one?
Big one.
Yeah, okay. At every next iteration, you choose the biggest of the pieces, and you keep breaking until you have 6. This takes forever. And we can also see it in the Beamer presentation. You keep going, and then you have 6. Finally, we have the independent random method. So in this method, you don't start with the stick of length 1. You actually choose 6 random lengths from a 0-1 distribution uniform, which basically means that you choose any length between 0 and 1. And these don't have to add up to 1. And so then you have 6 random pieces. So, pop quiz. Which method do you think forms the most tetrahedra? Who votes for the classical broken stick method? Okay. Anybody? Okay. Who votes for the sequential broken stick method? Okay, that's about half of you. Okay. What about the independent random method? 2 people? 3 people? 4 people? Okay. Who thinks it doesn't matter at all? Okay. So Alex is going to tell you about the results that we obtained and what we did to do that.
Okay, so as you can see, breaking sticks takes a very long time. And even if it were to take us only 1 second to perform each test, in order to get a sufficient data set to get good enough percentages, we need to spend too long on working on the project. So instead we use computers. In fact, we use one of our on-campus resources, the Illinois Campus Computing Cluster, to do this. We perform up to 6 billion Monte Carlo simulations in under around 3.5 hours, which is a vast improvement. So basically all the algorithm did was break a stick with one of the methods and check to see how many tetrahedra you get. Now when I say how many, I'm referring to the fact that given you have 6 sticks, there's more than one tetrahedron that can form because there are way more permutations of 6 sticks. In fact, there are 6 factorial permutations, meaning there are 720 possible tetrahedra. However, you have to realize that there are 24 symmetries, both rotational and reflections of those tetrahedra. So in fact, there are actually only 30 groups of distinct tetrahedra that we can test. So this is actually another optimization that we use. So all we need to do is check 30 permutations that we know are distinct and count using those. So again, we first ask what the probability is that we form at least one tetrahedron. And this table gives you the results. As you can see, the independent method is actually the most probable for giving you tetrahedron. So we determined that this is true based on what we consider degrees of freedom. If you imagine that the independent method, all the sticks are chosen independently of each other. So there are 6 choices to make, so 6 degrees of freedom. However, with the classical broken stick and the sequential broken stick methods, the 6th stick is actually determined by the lengths of the other 5 sticks, because their length is bound by the fact that their sum has to be the length of the original stick. So there's only 5 degrees of freedom. So that table, the first row represents the probability for at least one tetrahedron to form, and the second row represents the probability for the maximal number, or 30 tetrahedron to form, given a set of 6 sticks. Now, that second row can actually be found from a generalization of this problem. We next ask, what is the probability that we can form exactly k incongruent tetrahedra? And so we just had the computer program tally the results, and we got this bar chart, which represents the probability of exactly k tetrahedra forming, where k is from 0 to 30. So we noticed a couple peculiar things about this chart. We noticed that the even k always seem to have greater probabilities than their odd counterparts, and I believe 2, 6, 24, and 30 all seem to be outliers in the data set. They seem to be spikes in the graph. We determined that this can be answered by by group theory. However, none of us have actually studied group theory all that much, so we're going to skip over that. You can ask our faculty mentor afterwards about that. So now, Yulia is going to explain some of the applications of our research.
So as we said before, what we're doing is really a small subset of something that's known as the distance geometry problem. If you look at the triangle, that's the case when n equals 3, so what's the probability that you form a triangle? And the case n equals 4 is what is the probability that pieces form a tetrahedron. And the distance geometry question can sort of be summed up in this one statement. So you have n points, and n choose 2, or that's the same as n times n minus 1 over 2 distances. And what's the probability that you can just make a shape out of them? And you know, a lot of what we've been talking about doesn't really relate to the real world, or at least you don't think it does. But if you've ever used a cell phone or Wi-Fi, or you've called 911 and hoped that they can triangulate with your location, what they're doing is actually solving the distance geometry problem. Here, if you think of yourself and your cell phone as one node, a tower is another node, and a computer is a third one, what you can do to determine locations or the shape of the network is actually to solve your distance geometry problem. And another important thing is that this determines facets of molecular biology. If you look down here, this white area and this one down here are tetrahedral in shape. So if you think about the atoms as the nodes and their atomic radii, which is basically how close you can shove 2 atoms together before they just give up, as the distances, then we're also solving the distance geometry problem. So it allows you to figure out what shape a molecule can be and what different arrangements it can have. And this is really important to me because I drink a lot of coffee. But so what we've talked about today, just to sum up, is the original broken stick problem, how we took it up to higher dimensions, 3 dimensions, how this applies to the distance geometry problem. We talked to you about different breaking methods, such as the classical method, the sequential method, and finally the best method for forming the largest number of tetrahedra, which is the independent random method. And so these are some of our references, and thank you so much for listening. If you have any questions, please let us know.
Talked about like the molecular chemistry application. So it seems in there that not all pairwise distances are fixed. So is that a slightly different problem, or can you talk a little bit about that?
Basically the idea, like what we've studied is very simplified case of the distance geometry problem. It's where you have 4 points as opposed to many points. There are places like the hexagon and the pentagon where these situations don't work because it's not what we call a simplex. So the basic idea of the molecular biology aspect is that if you know the lengths of, or if you know the distances between atoms of methane or whatever that actually is, you can determine the shape of the molecule. But in our case, in the distance geometry case, it has to be in the form of a simplex or a tetrahedron in the 3D space.
Any other questions? Sure.
So instead of looking at simplices, have you thought about making like a regular polytope, so things like a regular polygon, say in 2 dimensions, or instead of a tetrahedron, things like an icosahedron, a dodecahedron, shapes that look like those?
So we actually did not consider those, but those are also applications of the distance geometry problem, right? So instead of, so what we have is this n choose 2 value that determines, so we have a point and 2 sticks are coming out of it. If you had, say, I'm so not good at shapes, but like at a dodecahedron, I believe you have 5 lengths coming out of from each vertice, so that would have to be n choose 5. So that's just a different case. It's not one that we considered because it wasn't a direct link from the original broken stick problem, but that's definitely something that you could look at using the distance geometry problem. Other questions?
Do you know how well that independent choosing method works for just the triangle?
Sure. So with the triangle, it would probably also work just as well, because if we go all the way back, that was something that was actually studied last semester by the same group. He was in it, and so you're still, it's the same length choice. So when you don't have to have them add up to 1, it's 3 degrees of freedom instead of 2 degrees of freedom. Yeah.
Since there's 5 degrees of freedom, could you solve, could you use a 5 degree polynomial?
Yeah, that would be one way to do it. Yeah, so if you think about, go back here, solving the bigger version of this matrix would actually be a 5 degree polynomial. Because when you solve the eigenvalues of a 5 by 5 matrix, it has 5 roots, and therefore by the fundamental theorem of algebra, it has to be a 5 degree.
So, did you solve it?
Well, I mean, I guess in solving a more complicated case called the Cayley-Menger determinant, when we took eigenvalues of that, we actually solved the 5 degree polynomials, but they don't have a closed form solution, like say the quadratic formula. Anybody else? Yeah, in the back.
So this extrapolated the broken stick problem from 2 dimensions into 3.
Correct.
Do we have, and this is probably going to be really odd, but I've heard of hypercubes, where it goes to a 4th. Any idea what the challenges would be extrapolating the broken stick problem into even higher dimensions, 4th of this?
Do you want to talk about simplices?
Yeah, so we do have a general definition of what a simplex is. You know, it's the collection of all distances between endpoints. That's basically what a simplex is. So we can represent the problem in more dimensions. However, there will be more permutations of tetrahedra or n simplices that you can create, and so it adds another layer of complexity because there are many more questions you could ask, like what is the probability that you could form a tetrahedra given n broken sticks, or what is the probability that you could form an n simplex given n broken sticks. So it does grow in complexity.
Anybody else?
Here's just a general question. So the way the distance geometry problem is phrased, it's not just can you create tetrahedron, can you create triangles. It just says here's these set of distances, can you find these points. Have you explored any other kinds of distances other than just Euclidean distances, like any other kinds of metrics?
So when we were actually querying this was something that we failed. So if we go back to the S matrix, if you don't have the condition that the three eigenvalues are positive, then basically what that boils down to is your tetrahedron or whatever shape you have doesn't have a positive volume or a positive area. So if you didn't restrict it to like a Euclidean space with what the traditional tetrahedron is, something with volume greater than 0, then yes, you would get complex numbers in it. But that doesn't really make sense and you can't visualize it. So I hope that answers your question. Anybody else? All right, well, thank you so much for coming.